Okay, this is actually convenient. This is after our long weekend. That the first slide just happens to be a review. So why don't I just go through what we've learned in the last couple of days, since it's been a while since we've been in class. All solutions have a certain concentration of hydronium. Pause. Why do all solutions have a certain concentration of hydronium? Well, what are solutions typically made with as the solvent? Water. Yeah. And what we've learned on this slide right here is that water ionizes 2 times out of every billion. Very slightly, but water has the ability to break up into an acid and a base. Which helps explain why water has a pH of 7, because we actually know the concentration of both of these two things. The concentration of hydronium ions is very small, 0.00000001. It's almost not noticeable, but there is a small presence of acidity in water. There's also a small presence of basicity. There's a small presence of base in water as well, right? Equal amounts. Really, the key here is whether you have more or less than this baseline right here. I would have showed you guys last week the idea that if this exponent right here is to the minus 7, then that's what helps you know that you have a pH of 7, right? Let me do a quick example here. What if I gave you a concentration, so let's say that your H3O amount, let's say that it was 1.5 times 10 to the minus 4 moles per liter. Before I go too much further, let's just talk through this without a calculator. Would you expect this to be an acid or a base solution? If it's got a concentration of 1.5 times 10 to the minus 4 moles per liter. Acid or base? Why an acid? You're right. Yeah, the exponent is less than 7, and by that it means that we have a higher concentration of acid molecules than neutral water would have, all because of this. Okay. Follow-up question. Estimate the pH. Just estimate it. Probably slightly under 4. The reason why is that this was 1.5. So like if it was 1.0 times 10 to the minus 4, the pH would be 4. But since it was 1.5, we're slightly more concentrated. But you got to remember how pH works. If you're slightly more concentrated, it means the pH drops a little bit. So I would expect this rough guess to be a pH of, say, 3.8. I'm just taking a guess here. Okay, well, let's say I wanted you to be precise on it. We're just not taking a guess here. Let's actually calculate that pH. Here's that formula. Negative log your concentration. So if I grab a calculator here, and we negative log 1.5 times 10 to the negative 4, we get a pH of 3.8. Hey, that was a pretty good guess. The formulas themselves are actually quite easy to work with. You just have to remember what you're talking about. If you have a higher concentration, it means the exponent is probably like a smaller negative number, right? Like negative 1 is more than negative 5. And if you have a higher concentration, you have a lower pH. If you can kind of wrap your head around that, really there's just two formulas here. Let me try the other one. What if I gave you a pH of 8.2? Acid or base? Base. Now, you probably knew that intuitively because you've learned in the past pHs above 7 are bases, right? But let's talk why. This 8.2 really means that you're looking at an exponent value up here of probably like 8. Does that make sense? Which means that if you're comparing to your baseline right here of water, which happens to be 1 times 10 to the minus 7 concentrations, comparing to that, you're actually less concentrated of acid. If you have less acid, it must mean you have more base. So then the other thing you could do is take 10, go to the power of minus 8.2. That's using this other formula right here. And that would then give you your concentration of acid. So 10 to the power of negative 8.2 gives us, so it was actually to the minus 9 actually. A big number though, but to the minus 9. This is definitely a smaller concentration than this is right here. Everybody okay with that though? Even though this is a 9, this is a smaller concentration than the 7. Then we learned about POH. POH is really silly because honestly it's the exact same scale as pH, only it's flipped. I think I even have a slide of that in these notes here. Where is it? Here it is. pH and pOH. No, it's not this one. Oh, I don't have one. I'll go back here. Here's one. If you have a pH of 14, you have a pOH of 0. If you have one of 5 and 9, or 4 and 10, what do they always add to? Yeah, 14. The only reason why the pOH scale is relevant is that it can help us calculate concentrations of bases. Let me take this guy right here. We know that 8.2 means it's a base, right? Could you calculate the concentration of hydroxide? Could you calculate the concentration of hydroxide? How would you do that? You're shaking your head. Yes. What would you do? If you have a pH of 8.2, there you go, yeah. So find the pOH. So what's the pOH going to be if the pH is 8.2? 5.8, because that's what adds up to give you 14, right? Okay. So then if you know that the pOH is 5.2, then those same formulas still apply here. To find your concentration, go 10 to the power of negative 5.2. There's our concentration of hydroxide. Is this concentration of hydroxide more or less than what water would be? Is this concentration of hydroxide more or less than what neutral water would be? More. Because to the minus 6 is actually bigger than to the minus 7. Right? So because this is slightly more concentrated than what 10 to the minus 7 would be, is this would be now a base. Wait, one more thing I got to show you guys. I skipped this the first time around. It's the rules for rounding pHs. They actually have a different rule. So if you want to maybe just write in a new slide here, there's a special rule for sigdigs of pH. So just kind of write this off to the side here, or maybe in the middle of that page there. Here's the rules for pH. Let's say I give you a pH of, say, 13.13. This has 2 sigdigs. Yeah. You only count numbers after the decimal place. It's a very simple rule, but you just have to remember to use it. pHs have a weird rule for sigdigs. Only count numbers after the decimal point. Okay, now let me explain why. Let's say I give you a pH of 13.13. First of all, acid or base? Very much a base, right? Should have a very, very low acid content, extremely low. In fact, I think I can probably predict how small it's going to be. By the time we're done, it's probably going to be times 10 to the power of minus 13, right? Because doesn't this 13 right here kind of help us know what power the exponent goes to? If I were to go 10 to the power of negative 13.13, see how this has a concentration of 7.41 to the minus 14? So I was close. It wasn't 13, it was 14. Okay. Well, this 13 right here, really in a way, here's what it represents. This number right here, if I wrote it out, goes 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's that number actually written out. This 13 right here really refers to how many zeros, essentially, you have in front of that number. Do those zeros count as sigdigs? No. Which is why we only count numbers after the decimal place in terms of your sigdigs. So this number right here, I would call it 7.4 to the minus 14. I would only count 2 sigdigs. It's an obscure rule. Kids always forget it. But if you're ever working with a pH, you only count numbers after the decimal place. Which means that if I were to give you a pH of 7, how many sigdigs does this have? None. This actually has no sigdigs. If I give you a pH of 7.0, you're going to have 1 sigdig. If I give you a pH of 7.00, you're going to have 2 sigdigs. Because what does this 7 here refer to? It refers to the fact that it's 0.00000000 I have one too many. One. Darian. It's a good answer. So when we're in our lab, when we're doing our labs, we should almost always be trying to measure things to at least one decimal place, if not more. Okay, which actually leads really well into our next topic today, because we're going to talk about how to measure pH better. Here, hold that thought here. I think I'm going to answer that over the course of today's lesson. Let me keep going here. Today's topic, if I can kind of skip through some of these review slides here, because really all of these were just review slides here. Let me start here again now. Our goal now is to be able to measure pH. Okay, because if we can measure the pH, we can then calculate a concentration. But Darian asks a great question. What if I tell you the pH is 5? Honestly, that's actually no good. A pH of 5, in the way that we calculate things, gives you no sig digs. We need more than that. So I want to talk a bit about some of the ways that we measure acidity. One of them is we use litmus paper. Right? But does litmus paper tell you exactly how acidic or basic it is, or does it tell you whether it's an acid or a base? It just tells you whether it's acid or base, right? Red is acid, blue is base, right? So you could use a pH meter. A pH meter works kind of well because that gives you 2 decimal places for 2 sig digs. There's a third method we use, and they're called the indicators. And you guys already actually know one of these indicators. It's litmus. Litmus, if we apply it to paper, litmus changes color between 6 and 8. But it's not just 6 and 8, it's 6.0 and 8.0. Hey. Sure. Okay. Litmus is actually an indicator. Okay. What an indicator does is it changes color based on the pH of a solution. And you guys should have recognized litmus because litmus on the acid side is red and on the base side is blue. And I think right now maybe the best way of showing you this is to tell you to grab your data books. Grab one of these here. I'm going to show you a chart in here we're going to use. I need you to go to page 10 once you find your book. Page 10. Okay, so this is a page of what are called acid-base indicators. And what they basically do is they change color depending on the type of solution you use them with. Okay? If you use, say, litmus actually, for whatever reason, is the one thing that's not written on this page. So I've actually got it in our notes here. Litmus changes color between a pH of 6.0 and 8.0. So if you have a solution that has a low pH, like say 5.3, 1.7, something below 6, litmus turns red. If you have a solution that is above 8, litmus turns blue. And if you actually have a solution between those, you have to use your basic grade 3 color theory and just merge the two colors. So what happens when you mix red and blue together? You get purple, yeah. And so the way indicators work is there's actually a 3-way color range. And they change color depending on the type of solution they're in. I'm going to show you guys this in a lab on Thursday. I've got a chart here. I'm going to skip ahead here. We've got this chart here of a whole bunch of indicators. And maybe it'll just work if I just try a little experiment here. What if you were to take methyl red, for example, here's methyl red, and you were to put a drop of methyl red into a solution with a pH of 9. Well, a pH of 9 would be up here. What color would methyl red turn? Would turn yellow. Do you see how yellow is kind of the top end color? However, what if you put that same methyl red into something with a pH of 3.0? Then methyl red would be red. But there's also like a fuzzy area in the middle here where if you put methyl red with a pH of, say, 5, it would actually turn orange. Yeah. Yeah, and so you can see how in this picture, all of these actually have a three-way color range where it goes like yellow to green to blue, or red to purple to blue, or yellow to green to blue. See how there's like always 3 ranges here? So these indicators, I'm going to go back a slide here. Indicators are very complex compounds. I don't even know that I could explain what they are. Most of them are organic, and they have like acid and base components to them. The basic idea, though, is that they change color depending on pH. And so I threw this picture in here to try to illustrate what you guys already know. When you guys work with litmus paper, there's actually an indicator of litmus soaked into that paper. You're actually using a drop of indicator soaked into paper. And basically the idea is that if the pH is low, litmus turns red, and if the pH is high, litmus turns blue. We like litmus because its natural range is right around 7. 6 to 8 means 7's right in the middle. But we can actually use indicators to help narrow down any pH based on our knowledge of how they change color. So I want to try a little activity here. Let's say that I gave you a solution. And what you did is you put a drop of indicator in 3 different times. I told you that orange 4 was yellow, Crescal red was yellow, and methyl orange is red. Let me walk you through how you might be able to solve this. I like using kind of a number line almost. She's like a number line here. So if you guys have your books here, find orange 4. Orange 4 is the 4th one listed. Can you guys see the range in which orange 4 changes? It goes from again. It goes from 1.4 to 2.8. Where is yellow? Is yellow the less than 1.4 or the more than 2.8? Yeah. So what I might say is that 2.8, we need this to be on the bigger side of 2.8. Now, I don't know exactly where the pH is, but I know it's definitely more than 2.8. So it could be 3, it could be 5, it could be 14 for all I know. But I know that it's on the larger side of 2.8. Isn't it again? That might help you from sneezing. As she has food like right in front of her too. She's gonna hit you. Oh, yeah. Okay, let's try another one here. It says that Crescal red is yellow. So if you guys can go to your table here, Crescal red is the second one. Now, Crescal red is actually a unique indicator. It still has its 3 colors, but it has a very large middle range. It goes from 0 to 1, it's red. Then from 1 to 7, it's yellow. And then above 8.8, it goes back to red again. Can you guys see that on Crescal red? There's actually 2 parts to Crescal red. It goes from red to yellow. And then later again, it goes from yellow back to red. So through what range is Crescal red going to be yellow? Anywhere between 1 and 7. So I might write that here and say that from 1 up until 7, so greater than 1, but it has to be less than 7. Because what would happen if the pH gets above 7? It would turn from yellow through to orange and then eventually red. Okay, so currently, where is our pH narrowed down to? What's the range we can narrow it down to? More than 2.8, but less than 7. Let's try a third one. Methyl orange is red. Methyl orange is the 5th one down, and if you can see on the list there, it goes from red to yellow, from 3.2 to 4.4. So if methyl orange is red, it means it must be below 3.2. So I could write like another one on here and say, well, at 3.2, it has to be lower. Can we narrow down a really effective range now? How narrowed down is this range? Anywhere between 2.8 up till 3.2. That's about where our pH is between. And so that's what indicators can do. But maybe to answer the question Darian posed at the beginning of class, it can't be just 3 or 4 or 5 because those don't have sig digs. We always have to measure something with at least 1 decimal place in a pH. Otherwise, we don't actually have a sig dig according to the rules we've devised. Okay, that was my first try at this. How did that work? Did that kind of make sense to you guys? Okay, let's try another example. If not, make sure you ask me later, okay? Sometimes I like to do what's called reverse shading. This is a math technique that I'm going to show some of you at some point. Maybe you've seen it already. Reverse shading is where I shade where the answers are not. And what ends up happening is it leaves what's left. Did we do this with you guys last year? Okay, so let me try another one here. It says phenolphthalein is colorless. Okay, if you can find phenolphthalein, it is the fifth one from the bottom. It says it's from 8.2 to 10, and so the colorless section is below 8.2. Can everybody find that information on their data sheet? If phenolphthalein is colorless, this means it's less than 8.2. So what I might recommend we do then is put an 8.2 on here. And when we do what's called reverse shading, I'm going to shade everything more than 8.2 and black it out. And basically what that means is this section here is where it's not. So 8.2 and greater is not where the answers are, but lower than 8.2, that's where the pH could be. Okay, then indigo carmine is blue. If indigo carmine is blue, this was actually redundant. Because you see how, gesundheit again. See how it goes 11.4 to 13? So if 11.4 is up here, everything lower than 11.4 would be valid, which means I should really just be reshading everything more than 11.4. And I've shaded nothing new. So actually that one didn't help at all. The last one here, phenol red is red. Okay, well phenol red, if you can find it, goes from 6.6 to 8. And the red is going to be everything more than 8. So why don't I put 8.0 right here? We're looking for everything that would be more than 8.0. So with reverse shading, what we do is I would shade everything that's on the opposite side. And what I'm now left with is a nice little narrow range. And I know the pH is somewhere between 8.0 and 8.2. Can you follow that? Okay, let's try one more. Methyl orange is yellow. So find methyl orange, it's the fifth one down. If methyl orange is yellow, yellow is everything more than 4.4. So I would say 4.4 goes right here. If I want it to be yellow, I'm going to shade everything below the 4.4 so that my unshaded section is the more than 4.4. So as of right now, I don't know whether it's 5, 6, 7, 8, 9, 10, 11, 12, but I know that it's more than 4.4. Right, thymol blue is yellow. Thymol blue is the third one listed, and this is another one of those tricky ones to read. Thymol blue goes red to yellow, and then yellow back to blue again. So if we're going to use it as yellow, it's got to be more than 2.8, but 8 is where it would start changing out of yellow again. So it's got to be more than 2.8, so I'm going to reshade the lower than 2.8 section again. But it's got to be less than 8. Because if it was more than 8, it wouldn't be yellow, it would be blue again. Okay, last one. Methyl red is orange. Hang on a sec here. Methyl red. It's the, seventh one down. Yeah, methyl red is not even listed as orange, right? See, methyl red, it says it goes red to yellow. Well, orange would be the hybrid of those. So really, if methyl red is orange, it must be between those two colors. So 4.8. And what's the other one? 6? If it's orange, it must be between these ones. So I would actually narrow it down to here and to there. Somewhere in here is where our pH then lies. This is exactly what we're going to do in our lab on Thursday, actually. I'm going to give you 3 solutions. I'm going to actually tell you what the pH is after you're done. Okay, I don't want you to know going in because that kind of cheats. But after you are done, I will absolutely tell you what the pH is. Okay, and I'm going to give you a whole schwack of indicators. And your job is going to be basically to narrow down the pH range. So if this turns red, then it means everything lower gets canceled. And if this turns yellow, everything higher. And eventually you narrow it down and narrow it down until you have hopefully a nice little narrow band. And you can say, I know the pH is between 1.5 and 1.7. Right? And you can slowly but surely narrow it down. And then for success on our lab, then when you're done, after you say, Chris, I think the pH is between 2.5 and 3.2, then when I tell you the actual pH, if it is between those numbers, then good job. If not, then something went wrong. Does that make sense? So Okay, that's actually it more or less for today's lesson. Indicators are a good way to narrow down pH. So really, we actually have 3 ways of doing this. You can narrow down a pH using litmus paper. But the problem with that is that litmus paper literally doesn't tell you anything about the pH. It just tells you whether it's acid or base. When you guys use that universal litmus paper, you know, the one that changed color from yellow to different things, the pH on that is also not very effective because literally it was just a whole number increment. We can't do any calculations with those. We need to have at least 1 decimal place. While using indicators, we get at least 1 sig dig. So that is another way that we can actually calculate a pH. The third way, probably the most effective way though, is if we have a pH meter. That would actually work the best. And that one actually gives you 2 digits. Gives you 2 decimal places. So, that makes sense? Cool. Okay, why don't I stop now? You guys have almost 50 minutes left here, something like that. Spend this time working on whatever it is you need to. Okay. Tomorrow we'll do our last lesson, and then that's it for the unit. After that, we're done learning curriculum. Okay.